Hi and welcome back. This is a continuation from my previous tutorial video on the designing of the speed controllers for DC motor drive. Okay, in this tutorial I will be showing you how to design the controllers for speed control DC motor drive with inner torque loop or current loop using CISO tool or controlSystemDesigner. However, unlike the previous tutorial video, I will construct the transfer function or the loop transfer function in Matlab rather than obtaining it from Simulink like we did before. The same parameters of the DC motor will be used in this tutorial. This is the transfer functions of the DC motor that we have constructed earlier based on the four equations shown here. The armature voltage equations, the torque equations, the torque speed, mechanical speed equations, the back EMF equations. In order to obtain the transfer functions between the torque and the armature voltage VA, then we have to do the transformations of this block diagram as shown here, which eventually we will obtain the final step of, or the final form of the block diagram, which is shown here, which gives us the relationship between the armature current and the armature voltage, or the torque and the armature voltage. So right now I will construct the transfer function, the final transfer functions here between the torque and the armature voltage, because what we want to do first is to design the controller for the torque loop. Okay, and then we will proceed towards the output. This is exactly the same process that we have done before in our previous tutorial. Okay, let me define the parameters for the DC motor first. And then let me define the loop transfer functions for the torque loop, which is the combinations of PI controller for the torque loop, the power electronic converters, the DC-DC converters, which is just simply a DC gain that we have discussed earlier in the previous tutorial. And this is the transfer functions between the armature voltage and the torque. Okay, so I'm going to write down the loop transfer functions by setting the PI controller as a unity gain. The gain for the converter in our example here is going to be equal to 12 because the DC voltage is 60 volts and the triangular peak value is 5 volts. So 60 over 5 is 12. GDCM is the transfer functions between the torque and the armature voltage. Okay, so the loop transfer function is just a multiplication of GDCM with 12. So GLT, which is the loop transfer functions for the torque, is just equals to 12 times GDCM. Okay, now I will start the controlSystemDesigner or CISO tool. Okay, this is the controlSystemDesigner window. There are several plots here. We have the body plot for the loop transfer function, and then we have the root locus editor for the loop transfer functions. These two plots can be used to tune the PI controller, and then we have the analysis plot, which is the step response plot. In this tutorial, what I will be doing is to tune the PI controller for the torque and as well as for the speed using the bode plot based on the loop transfer functions. Okay, which means that I don't need this root locus editor, so I'm going to replace this or just remove that, and then I'm going to add the analysis plot of the closed loop transfer functions, which means that I'm going to choose the R to Y IO transfer R to Y, which is the closed loop transfer functions from here to here. These closed loop transfer functions is useful, especially when we want to select or determine the closed loop bandwidth. Alright, and for the torque response, I don't actually need this step response as well, because what is ultimately that we want is the response of the speed. So in that case, I will also remove this analysis plot, which is the IO transfer function step plot, and replace it with the new pole 0 map. Okay, for the loop transfer functions, which means that I'm going to choose the loop transfer and then plot. This will give me the locations of the poles and zeros of the loop transfer functions. From the bode plot, you can see that there is 1 0 here and there are 2 poles here, which corresponds to 2 poles and 1 0 there. Okay, the locations of the poles are determined by the characteristics equations of the loop transfer functions, which is given by this equation here. As you can see that the transfer functions of the torque and the armature voltage contain 1 0, which is located at B over J, and the poles are determined by this denominator of these transfer functions or the characteristics equations. We can know the values of the zeros and pole, or the locations of the poles and zero, by just putting that cursor to that pole. One of the pole is located at 348 radian per second, the other one is at 36.4 radian per second, and we have a 0 which is located at 0.0658. These poles and 0 is exactly the same as what we have obtained in our previous tutorial using the Simulink blocks to model the closed loop system. If you recall from our previous tutorial, we have set the frequency of the triangular wave to be at 20 kilohertz, and according to our rule, then the closed loop bandwidth of the torque has to be a decade lower than this 20 kilohertz, which is 2 kilohertz, and which is equivalent to 12.56 kiloradian per second. So we have to select the values of the Kp and Ki for the PI controller so that the crossover frequency occur at 12.56 kiloradian per second, or the closed loop bandwidth of the torque to be at 12.56 kiloradian per second. As I have mentioned in my previous tutorial video, that when we add the PI controller to the loop, then we will add a 0, an integrator, and a gain. Okay, and we have a choice of selecting the locations of the 0 for the PI as well as the gain by manipulating the values of Kp and Ki. So let's do that now. Before we do that, I will set the control requirements on this closed loop bode plot. Okay, so you just right click there and then you set the design requirements, new. I'm going to go for a very low frequency, and then the magnitude is going to be at -3 dB, because at the closed loop bandwidth the gain of the closed loop is equal to -3 dB, and the frequency is going to be at 12.56 kiloradian. Magnitude again is going to be at, I'm going to set equals to -3 dB. Alright, and then I'm going to set constraint system to be larger than this bounded area. Okay, which means that we have to make sure that the gain is equal to minus 3 dB at the closed loop bandwidth of 12.56 kiloradian per second. Let's do that now. So I'm going to add an integrator first. Okay, and then I'm going to add the 0. So what I will do is I will choose a 0 in between these two poles. Let's say that I put it here. Okay, then as you can see now that the phase margin is equals to 91 degree and the crossover frequency is very, very low, which is at 0.0012. So now I'm going to increase the gain. I'm going to increase the gain. As I increase the gain, then the closed loop plot also changes, and what I will do is I will zoom to this particular point or frequency at 12.56 kiloradian where the gain is minus 3 dB. So I will keep on increasing the gain now until I get that minus 3 dB at 12.56 kiloradian per second. So it's about that, right? So you can see that here the frequency is, the crossover frequency is at 12.8, which is more or less close to the 12.56 kiloradian per second. So that completes our top controller design as far as the bandwidth is concerned, and the phase margin is good, which is at 91.1 degree. And as you can see also that the DC gain is very large, which means that the steady state error for the top should be equals to 0. Before we finalize the design of the top controller, I will round off the values of the controller that we have designed. So you right click here, you go to the edit compensator. So this is the values of the controllers that we have designed. As you can see, this is the gain, this is the 0 locations, and this is the integrator, which is a PI controller. So instead of 7,579, I will round off to 7,580. And then the locations of the 0, I will round off to 136. Okay, now I will export the PI controller that we have designed to Matlab workspace. So you go to the export and we select the C, which is the controller, and we export it to the Matlab workspace. Okay, let's go back to the Matlab window. As you can see now that C is there in our workspace. So if I just type C, this is the transfer functions of the PI controller that we have designed. Alright, now we are going to design the controller for the speed loop, which is the outer loop. And as we have discussed in our previous tutorial, the closed loop bandwidth of the speed loop has to be a decade lower than the bandwidth of the top loop, which is at 1.256 kiloradian per second. Before we do that, we have to update the loop transfer function for the torque with the new values of the controller that we have designed, which means that our GLT loop transfer functions for the torque now, which is a new one, let's just put n there, is equal to G times C. Okay, so this is the loop transfer functions for the torque. Okay, so if you look at the block diagram here, if we want to design the PI controller for the speed here, then we have to obtain the equivalent open loop transfer functions for this top loop. Okay, we already have the loop transfer functions for the torque, and then we can just easily obtain the equivalent open loop transfer functions for this top loop. which means that the G closed loop of the top. Okay, so this is the equivalent open loop transfer function of the closed loop torque. If I cancel out this integrator and a 0 at the origin, and then I cancel out the 0 at 36.4 and another 0 at 348.3, then I will left with only two zeros, which is at 136 and at minus 0.06579. Okay, and the pole, so we only left with a pole at minus 134.4 at minus 13.11 kiloradian second and at minus 0.06532. So let's do that now. GCLT new, which is the closed loop torque transfer functions. Okay, so if we go back to the plot diagrams here, the speed loop transfer functions will consist the torque closed loop transfer functions, which we have just defined just now, and then we have 1 over Sj plus B, and of course the PI controller. Okay, and again we are going to set the PI controller as a unity gain, which means that the speed loop transfer function is just a multiplications of the torque closed loop transfer functions and 1 over Sj plus B. So I will define the loop transfer function for the speed, GLS, as equals to okay, so this is our loop transfer functions for the speed. Now I'm going to open another window of Control System Design tool using GLS. Again, I'm going to remove this root locus editor and replace it with the closed loop body plot. I'm going to plot from R to Y. And let's look at on the pole and zero of these loop transfer functions, because from this body plot you can see that there are several poles and zeros located here. To exactly know these locations, then I'm going to use the pole zero map. Of the loop transfer functions. So there is one pole here at 13.1, and then there are several zeros and poles here. So I will zoom it now. Let's look at on these poles and zero here. So we have a zero at 136 minus 136, which is very close to a pole which is at 134. Okay. And then we have a very close zero and pole as well here. You can see there is one pole here at 0.0653, and then there is a pair of zero and pole here. So if I zoom it, that poles and zero, then I can see that it is at 0.0658, and another one which is zero at also 0.0658, which can be considered to be cancelled out each other. Okay, so we have a pole here which is due to the J and B, and then we have a pole and 0 which is cancelled out, and we have another pole here which is at roughly equals to the closed loop bandwidth of the torque. So I'm going to add the grid first, this body plot, and I'm going to set the control requirements for the bandwidth, which is at 1.256 kiloradian per second, to the closed loop body plot. So right click here, new, alright, so I'm going to put a very small frequency here, and then the magnitude of minus 3 dB, frequency of the bandwidth at 1.256 E3, magnitude of minus 3 dB, and then to be system to be larger than the bound. Alright, so we have to make sure that the closed loop bandwidth is going to occur at that frequency, which is at 1.256, which means that the gain of the closed loop has to be minus 3 dB at this closed loop bandwidth by tuning using these loop transfer functions for the speed. And again, if I add a PI controller, then I will add 3 elements, which is DC gain, an integrator, and 0. So let me add the integrator first here. Alright, and then I will have a choice of selecting the 0. And I'm going to place a 0 which cancels that system pole. So it's going to be exactly there. Alright, so I will now adjust the gain so that the bandwidth will be at that point. So I'm going to zoom around this area here, and then as you can see that the crossover frequency right now is larger than it should be, which is at 1.256. So I'm going to reduce the bandwidth now, which is going to be around that 1.13, yeah, almost 1.256, around that. Okay, so that is going to be the closed loop bandwidth, which is at 1.2 kiloradian per second. And I'm going to export this to the Matlab workspace. Before we do that, let's look at whether we have fulfilled the requirements here. If you look at the step response now, this is the step response of the speed. However, you should remember that as we have discussed in our last video, the step response is not actually giving us the actual response, because during acceleration the torque will reach the limit, and therefore our linear model is no longer valid. And then we have the closed loop bandwidth of at 1.2 kiloradian per second with a phase margins of 84.7 degree, which is larger than our requirements of 65 degrees. Okay, now I'm going to export the speed controller that we have designed to the workspace. And I'm going to differentiate that from the torque controller that we have designed previously with CSP for the speed. Sorry, I have to select that first. Okay, if you go to the Matlab workspace, you will see now we have two controllers, C, which is for the torque, and the other one is CSP for the speed. What are the values of KP and KI for these two controllers? If you look at the transfer functions of the PI controller, you can see that we can write the transfer functions of the controller in terms of gain, which is KP, and a 0, which is located at KI over KP, and an integrator. So let's look at the top controller first. In this case, then the values of KP for the top is going to be equal to 55.735, and the values of KI is going to be equals to 136 times 55.735, which is roughly equals to 7,580. Okay, so again the values of KI for the top controller is 7,580, and the values of KP is equals to 55.735. Let's look at the speed controller. Comparing with the PI controller transfer functions, KP for the speed is equals to 0.18636, and the values of KI for the speed is 0.18636 times 0.0667, which is equals to 0.01243. The next step is for us to verify this controller using large signal simulation, and we are going to use exactly the same model as we have done in my previous part 2 of the tutorial. Alright, now I'm going to verify the controllers that we have designed using the large signal simulation model. The verification is necessary, as we have discussed before in our previous tutorial video, because the controller that we have designed is based on the averaged and linearized model of the system, and we have to make sure that they actually work with the actual system, which is a nonlinear system. The large signal model that we will be using here is exactly the same as the model that we have used in part 2 of the tutorial, which is based on unipolar switching scheme. In my previous tutorial video, I have explained in detail the large signal model, so I'm not going to do that again here. So let's type in the values of KP and KI for the torque and speed of the PI controllers that we have designed before. Let's go for the torque controller first.
It's 12:15.
Okay, and let's do for the speed controller now. Okay, just to show you again, this is the triangular wave generator. If I click that, then you can see that the frequency is set to 20 kilohertz, and the peak values of the triangular is at 5 volt. And the parameters of the DC motor is exactly the same as what we have used in designing the controllers. Okay, and the reference speed that I'm going to use is shown here, which is similar to what we have performed in the verifications of our controllers in part 2 of the tutorial video. Okay, so I'm going to run the simulation now, and we are going to look at on the speed and the torque response. The speed, which consists of the reference speed and the actual speed of the motor, and the torque is coming from the top of the motor. So I'm going to run that now. This is the speed response, which consists of the reference speeds and the actual speed. The reference speed is in yellow and the actual speed of the motor is in green, and the bottom trace is the torque response. As you can see that the speed follows the reference with an acceleration from 0 to 150 radian per second here, and decelerate and reverses the speed here to minus 150 radian per second. And then there is a step change in speed reference here, and the motor accelerate to from minus 150 to 150 radian per second, with the acceleration torque limited by the saturation block here, which is set to 1.5 and minus 1.5. Okay, and the motor is decelerate to 0 here with a step change in the reference, and again the torque is limited by that saturation block, which is at negative 1.5 Newton meter. If you zoom in the torque response here, for example, then you can actually see that the torque is basically contains ripple due to the switching of the converters. Okay, so I think that is all that I want to discuss here, and I'll see you next time. Thank you.